Good morning. Thank you for the invitation to talk. I'm looking forward to telling you about experiments we do at the University of Wisconsin. And it'll be experiments that are done on two devices. Originally, the title of the talk was In the Big Red Ball, which is our main facility, and I'll show you that. But before that, we were doing experiments on a device called the line tide reconnection experiment, which is what led to the new experiment. So I'm going to go through that, and you'll see that we have a very nice system for creating a model 2D MHD turbulence environment where we can control the injection scale of energy and study how the system evolves. And so that's kind of where I think I connect most directly here. My talk's going to be in about two different things that are related to flux ropes. One is this model system. In the second half, I'm going to tell you about new experiments that we've done where we create a Parker spiral in the lab, and at the interface between the magnetically dominated coronal region of a model star, plasmoids, flux ropes are ejected out into something like a solar wind, and I'll show you that also. So these are related themes, but it's two different talks, and I think you'll find them both interesting. Okay, so what is a flux rope? Roughly speaking, a flux rope is is some magnetic volume where we're inspired by something like the coronal loop on the surface of the sun, or perhaps long bundles of flux in the solar wind. These systems can carry current, and so this is not working well enough. I'm going to have to move to this, sorry. Along these magnetic field lines, some current can be injected. Current injected creates twist to the field. There's a short magnetic field the short way around, and that twist leads to lots of phenomena. For example, if there's a lot of current, this flux loop will become unstable and lead to something like a coronal mass ejection or a flare. Internally, if this twist it can become dynamic, and one can have fluctuations in turbulence, which lead to things like heating. And so studying these systems might be good for studying flares, but it might also be good for studying something like the Parker problem, where the heating of the corona is involved. Okay, we do experiments on two machines. This is the first experiment machine, and this operated well before this, is called the line tide reconnection experiment. And what it is it's what we would call in the field a screw pinch. So very, very simply, it's a solenoidal magnetic field, and we inject current along the column, and injecting current creates twist, leads to instabilities, and so forth. And so this is really very simple. The big red ball, what we've done is now we've taken this geometry and we've put anodes and cathodes at each end. We send current through the machine, and we can create flux rope turbulence inside the machine. And I'll show you that geometry as we go forward. So these are both vacuum vessels, so a cylindrical vacuum vessel. This is a big spherical vacuum vessel. The special feature of this is that it has some 3,000 very super strong permanent magnets that allow us to confine a hot, fully ionized gas inside without too much neutral gas. So we can make a plasma which is almost completely ionized, even without a magnetic field. Because these permanent magnets cancel when you go close to the center. But we can also apply a large-scale field and create plasmas which go from pressure-dominated, very, very high beta plasmas to magnetically dominated, where the magnetic field becomes the most important part of the system. And so I'll show you experiments from there in the second half of the talk. Okay, so what are we trying to do? So very simply, if you have a guide field and you introduce current, there's a twist that develops in the field, and we have something called the safety factor, which is the inverse of the angle that governs how much the magnetic field twists. And if there's enough twist, which is this parameter here, enough current dropping the safety value Q low enough, this system becomes unstable to a kink mode. It kinks up, basically a flare, if you will. And so by injecting more and more current, we can study the stability of this system. And this is where we started. Initially, we built the experiment to study a very, very particular version of that kink mode. And the particular version of it is that in something like loop on the sun, the twist is created by vortices. And if you think about an isolated vortex in the photosphere twisting, the magnetic field is frozen into the highly conducting fluid. It twists up. A vortex, if you go far enough away from the center of it, has no twist whatsoever. There's no velocity. If you go close in, it's twisting. What that means is the twist of the field's far away, which to some extent by Ampere's law is the amount of colloidal field that you have going around, is zero. There's no net current inside a flux loop which has just been twisted by a vortex. If you go far enough away, there's no twist. Inside there's twist, and then of course there's a magnetic axis somewhere. This equilibrium is a special type of equilibrium which has never been studied in experiments. We'll call it zero net current. The idea being that a vortex twisting has no net current. You have current up in one direction in the middle and return current on the outside. It's like a coax of current, if you will. And so this experiment was built originally to test the following two configurations. So what we have is we have a gun array that injects current from a number of discrete guns. And at one end of the experiment, we have this array of guns which are injecting current. And at the other end of the system, we had current injected the opposite direction. And so I'm just going to show you this because it's the motivation for the original experiment was to inject current one way up the middle, return current on the outside, create a coax of current without any net current, and study the stability of that. That's different than something like a tokamak where you drive current all in one direction and you drive it with an electric field which you can only control from the boundary. And so this was the only way we could get at that experiment. So that's the special feature of this device. So I'll show you results from that, but then what I'm going to show you is that by turning individual current channels on and off, we can create a very unstable MHD system where essentially I'm injecting current at whatever K value I want. That injects energy at some particular value of wavelength, and the turbulence that develops is kind of like what you would study in simulations, I would say. Okay, so we inject current. I'll show you experiments here where we inject current from several of these cathodes. What they tend to do is twist up because the magnetic field is twisted, and they smear out and create smooth currents if you inject from all of them. We can measure what the current profile is using an array of some 300 probes at the middle of the experiment. And so I'll show you movies where we measure the current density that goes down the column of this thing from a bunch of discrete measurements. And this just shows you the scale. It's very small. This is the magnetic probe that's inside these tubes on a quarter, so it's very small. And so if we inject current from these cathodes, this is what the sort of average current density profile looks like. It's about 10 centimeters across, relatively smooth, and we can turn off the inner and outer ring or even drive current in the negative direction and control the current profile. These are the sorts of things that we'll get from that. I'm going quickly here because I want to show you mostly what the movies look like. So this is the zero net current experiment we started with. This is a current injected in the central gun. This is the current injected from a set of 6 guns just outside of that. And this is the total current, which is almost zero. And so this was the first time this kind of current profile had been created. What we found was it becomes wildly turbulent. It fluctuates a lot. There are lots of fluctuations. And this is sort of the amplitude of the m=1 mode that turns on when we drive enough current, when the Q drops low enough to create this instability. Azimuthal mode. And this is what the movie of that looks like. And so this is the current density measured at the center of the machine, and you get the sense that actually it's not that interesting. It's not that wildly unstable. It's not really, the fluctuations are small, and it just kind of sits there. What's happened actually is this instability is localized at the region where the current goes from negative to positive, and it's kind of confined, okay? So if you're trying to study turbulence, this might not be the perfect system. And we thought, could we do something that's more interesting, more dynamic, if you will? And so we decided to try something a little different, which is to turn off a bunch of guns and now inject current from three different locations, 3 discrete current-carrying tubes that interact nonlinearly and develop into I think is a more interesting system. So you can think about this as injecting magnetic energy into the system by controlling the spectrum of the current from one end of the machine. And I'll show you two movies that show two different injections, if you will. So this is a system where we turned on current in two loops and we just let them interact. And this is sort of what you see as far as fluctuations in the current density are concerned. And so this is a relatively dynamic system, and I'll show you spectra and wave number spectra in a second. But the point is, it's much more dynamic than that simple axisymmetric equilibrium that I showed you previously. We can do the same thing with 3 flux ropes, and so here's 3 of them. It becomes actually quite a bit more interesting, I would say. In what follows, I'll show you primarily spectra from this configuration. So very highly fluctuating. The amplitude of the fluctuations is at least the same level or more than the equilibrium field, depending on where you look. It's a highly turbulent system. Okay, so we can study a lot of different things. When the magnetic field is very strong, the current channels tend to, on average, remain localized and together. As beta increases and the fluctuation amplitudes become even larger, the currents tend to merge. On average, this represents an inverse cascade of magnetic energy. The magnetic field is starting to smooth out at longer wavelengths, and you can actually quantify this in terms of a perpendicular wave number spectrum, where what we show is we inject energy at about this spot, and we can find energy showing up at large scales, and also there's a cascade to short wavelengths.
Is this averaged over averaged over the time you run the experiment, or is this just
It's average. This is the average over a long pulse of what the fluctuations are, and this is just for 2 simple cases where we turn the magnetic field to be strong and weak, and as we allow the system to be more dynamic at low field.
What are the betas?
This would be beta of maybe so the high B case might be a beta of about 10%, and the low B case would be a beta of around 1. And we would like to go further than that. I'll show you where we're heading with this. Okay, and so we've now moved this experiment over to the big red ball, the configuration I showed you before. So this is a 3-meter diameter vacuum vessel, and we can put the gun arrays on either end. This gives a lot more freedom for the flux ropes to bounce around inside the middle of the machine. And what we can also do is we can change the geometry a little bit so that the magnetic field is not perfectly straight, but becomes what we call a mirror. So the magnetic field is strong at each end of the device. It gets weaker in the middle. In the weak region in the middle, the beta is very large, up to 10, maybe 100 in some cases. But it still has this current to drive the fluctuations. And I can show you, this is a movie of what you see when you look at the anode end. So this is the flux rope turbulence, if you will, as viewed by a movie. And the magnetic movie that I showed you earlier, which was done on the other machine, essentially is capturing the same type of dynamics. Okay. So these experiments are just beginning. We're just beginning to look at things like frequency spectra. This is the magnetic spectrum, and this is the density fluctuation spectrum. We find that you can fit whatever power law you want to this, but we see that this is about where the injection is. We think there's dissipation happening at around the ion cyclotron frequency, and above that, things are heavily damped. And because it's compressible turbulence, there are density fluctuations also. we're very interested in studying how energy is divided between electrons and ions. That the energy of the turbulence is dissipated. There are theories about how the energy dissipation depends upon beta and the ion temperature. So we got started looking at electron temperature and ion temperature profiles, and we find is that the ions are anomalously hot in this plasma. And so evidently the heating is not coming from the current, which is primarily heating the electrons, but rather through something like viscous dissipation. And so what I would say to you is these experiments are ripe for starting to look at with theories, and moreover, if you're interested in this, we would love to collaborate on studying how this magnetic energy is dissipated. I would point out that we operate this big red ball as a user facility for the Department of Energy, and we're looking for external users who would be interested in coming in, helping us lead experiments that we can then help you with in your data analysis and so forth. So this is the type of platform, the type of experiments we might be able to do. Okay. Okay, so now I'm going to change a little bit, and I'm going to tell you about some experiments that we've recently done where we've created essentially a Parker spiral in the lab, and there are flux ropes related to this also. Okay, all right. So this is so let me just remind you, in the center of the solar system, and so you guys know this better than I. There's a star with a magnetic field, and the magnetic field of the sun is strong. Close to the star, and oftentimes it comes in closed loops that start on the surface and return to the sun. When you move far away from the sun, the magnetic field is weak, and there's a solar wind that's developed at some point where the plasma of the breaks away from the gravitationally and magnetically confined plasma in this region. At that point, where the kinetic energy density of the flowing plasma becomes larger than the magnetic energy density of the magnetosphere of the sun, the plasma transitions from a regime in which it's magnetically dominated to one in which it's flow dominated. In the flow dominated region, the plasma inertia is able to take the magnetic field lines of the star, pull them outward, and inertially carry them into a geometry that's come to be known as the Parker spiral. So there's this Archimedean spiral where the wind is carrying the magnetic field lines outward. The conservation of angular momentum as you move out causes them to twist as the star rotates inside that frame. And we're interested in a couple of things. Like, one is, what can we make this current sheet in the lab? Can we study its stability? Can we study the transition where the plasma goes from closed field lines where it's confined to be in a region on a field line like this to the open region? How does plasma get transported to fuel the wind that might develop in that equatorial sheet? This would be, for those who know, this is related to the origin of the slow solar wind. And we had this idea to create this artificial magnetosphere in the lab by putting a permanent magnet, a dipole that makes up a magnetosphere in the middle of the experiment. Imagine a big plasma atmosphere where we now have a magnetic field, a dipole in the middle, and we can draw some current from a cathode here to some anodes on the outside of the sun. So what does this do? Current will then flow. The electrons are moving out. The current is flowing in. The current crossing the magnetic field lines causes a torque on the plasma. The torque causes it to spin. And so what we can do is we can make this magnetosphere spin. We've done lots of experiments along these lines. We can, by applying this torque to the plasma, we make it rotate. So our idea was, can we make this region spin very fast and make it spin so fast that in some region here, the rotational velocity is larger than the Alfvén speed, or equivalently, there's a point in here that we'll call the Alfvén point, where the flow speed equals the Alfvén speed, and the plasma transitions from magnetically dominated here in the center to flow dominated in the outside. So at some level, we're just trying to create an interface between a magnetically dominated and a flow-dominated plasma and see what happens at that spot. So the magnetic field, of course, drops off very rapidly, and if you plot the Alfvén speed that goes with that magnetic field, it would look something like this. It becomes very low. It's on the order of 10 kilometers per second. This isn't so fast. It's actually relatively easy in this region. When you go very far in, the Alfvén speed is enormous. It's magnetically dominated. And we can create plasmas which spin kind of as a rigid rotor up to 10 kilometers per second or so in this configuration. And so this is the conjecture. And this is what happens in that case. So this is actually the result from an MHD calculation. A current sheet is developed in this region in the azimuthal direction that causes the magnetic field lines to be stretched out. The ones on the top point outward. The ones that point below the equatorial sheet point inward. And this causes overall twist. There's a very interesting point here. This is the point where the magnetic field actually goes to zero. You could call it a Sieradzky layer. It's a special Y point in magnetic topology. And studying what happens there is super interesting. In fact, I'm not going to go into it in this talk, but there's a whole NASA mission called Parker Solar Probe, which is essentially trying to understand what's happening there, and that's flying towards the sun even as we speak. Okay, so this is where it goes inside the machine. Then we have a bunch of these probes that we can use for measuring robotically, scanning the probe through slices to measure and map out what the structure of the magnetic field is that develops out here. So, okay, I still have 13 minutes. Okay, and I'll point you to this. This is the recent publication that came out. Okay, so that was the cartoon of how the experiment would work. This is the result of an MHD simulation of that same configuration. We can inject current. In the simulations, this is straight up MHD with the experimental parameters for density and temperature and so forth. What you get is you get poloidal flows that develop like this into circulation. So it's a little different than the solar system. We're a closed system with boundary conditions and so forth, but this gives circulation like that. This is what the toroidal or azimuthal velocity is. This would be like the rotation within the disk. We find that the magnetic field gets distorted out. There's a Y point here. And if you plotted the magnetic fields just above the ecliptic, like here, this is what the magnetic field geometry would look like. That's the Parker spiral. And in 3D, this is what the rendering of that would look like.
So in Parker's original model, I guess the magnetic field lines are supposed to come back from infinity?
They essentially have to, right. I mean, to the extent that it's a simple 2D model. In fact, right. So this is how we do the experiment. It's super simple. We have a capacitor bank, a switch. We drive we apply a voltage to these cathodes, and we have the return current coming from some anodes. So there's a circuit, if you will, where there's current flowing up through this rod and down through this rod. Of course, that creates azimuthal field, so that's part of the generation of the twist, if you will. But it's but out here in the plasma, the current is something we can measure. Okay, so this is just showing what happens, and I'll show you the movies here in a second. So we'll make measurements of the magnetic field and everything else in some pie-sliced segments. We step the probe from shot to shot and measure the average development. And this is a movie of what you'd see if you looked in the experiment. So this is about at the Alfvén surface. There's a big current sheet developing there. These cathode spots are just places that get hot, but they do give a little extra current that you can then see spiral outward. And so there's already some signature of the large-scale magnetic geometry coming from that. So we make measurements with these probes, this kind of thing here. This is what the vacuum magnetic field would look like from the dipole that we have in the middle. We make measurements at all these positions, and then we build up movies. And we can also put, so if you look from the top, this is the dipole in the middle. We can have cathodes and anodes. These make the plasma. We can make measurements at different different positions so we can study how axisymmetric it is. This is what one has for time traces. We inject the current. It goes up to about a half a kiloamp and then decays away with time. This is the capacitor bank discharging. And if you look at the signatures of everything, what you find is that there are basically two phases, and I'll refer to these as we go forward. There's one which we'll call a turbulent phase, where the current is large and driving lots of fluctuations. And then there's what I'll refer to as a more laminar or a coherent phase, where we can see the individual modes that ultimately we believe lead to the turbulent phase. And I'll explain and I'll show you simulations that kind of show how there's a transition from laminar to unstable to turbulent as we go from low to medium to high current. Before we go there, I'll just show you this is what the magnetic field looks like without any current, the vacuum field. This is what it looks like with current. You can start to see on average how it's being stretched out. The color contours are showing the current density in the azimuthal direction, which are causing the stretching of the field line. And if you trace out this field line at the top, you start to get the twist, which is the twist of the Parker spiral. That's what the average magnetic field is doing. If you plot along this ecliptic plane here, what the measured velocities and magnetic fields are, this is what the Alfvén velocity would look like. Our toroidal rotation gets up to about the Alfvén speed. So we have a system where the Alfvén speed and the rotational speed are about the same. It has an Alfvén Mach number of approximately 1. It's about half magnetically and half flow dominated in this region. It also there's a big pressure gradient which develops due to the confinement of the dipole here in the middle. Now, going to the fluctuations, if you look at the frequency spectrum versus time, this is the high current phase, this is the low current phase. What we find is that there's very broadband turbulent fluctuations early when the current is strong, and then this sort of goes into a single mode whose frequency changes with time. And so if we average over all shots, we find that there's strong correlation from this mode, and that's something that we can then study experimentally by measuring the correlation between probes to build up a map of what's happening during this phase. So let me first begin with this single coherent mode and show you what that mode is. And I'll show you data from this region here where I don't have turbulent fluctuations, but I have very reproducible unstable modes that I can actually image. And this is what we find. We find that the fluctuations are localized to the region about where the Alfvén point would be, the point where the magnetic geometry is changing from the dipole to maybe something like the field line here at the middle. Those are big fluctuations. If we look at individual probes, they're oscillatory. We can measure amplitudes and phases for all the signals. And what we find is we're actually ejecting little plasmoids, flux ropes, which are azimuthally symmetric modes that break off from the closed flux surfaces of the magnetosphere and actually fuel the outgoing wind. And this is showing the density fluctuations, and on top of that, you were seeing the magnetic topology as it breaks off. And so we think that this is a model. I can get into that in a little bit, but this is, roughly speaking, a model for how something like the slow solar wind would be fueled. This is indicating that there's transport from the closed field lines, which are connected to the dipole, to the open field lines, which then propagate outward. Okay, so a few key points here. These represent a bursty radial flow of plasma at about the Alfvén speed. The plasmoids are sub-ion scaled. Because the density in our experiment is relatively low, the ion skin depth is big. That's sort of one of the problems with laboratory experiments. And so these are things happening at the electron scale. We don't actually, so now I'll get into simulations and so forth. In simulations, these plasmoids are not observed in straight up MHD. We have to include Hall terms. For those who know the difference between those things, the Hall MHD is actually critical here. And there's a strong correlation between the magnetic and density fluctuations. Okay, and this is just a little bit of that comparing experiment. These are the flow speeds and the magnetic fields with MHD and Hall MHD. The geometry in Hall MHD is closer to the experiment. Similarly, in the flows, we find that the flows between Hall and MHD, Hall and experiment are probably closer matches. All three cases advect the magnetic field out, but there's a big difference between the Hall and the straight up MHD as far as the ions are concerned. Okay, so now I'm going to show you, so this is the experiment that I showed you. The fluctuations for these coherent modes was about 20 kilohertz. We have a code that's used for modeling fusion experiments called Nimrod at the University of Wisconsin that is very convenient because it has toroidal geometry, and you can put actual experimental parameters in and match all of the dimensional numbers exactly and compare so that frequencies which are measured would correspond to the same type of experiments parameters in the experiment. So this is a simulation in using Hall MHD of what happens dynamically. You could see the fields get stretched, and then there's this periodic bursty plasmoid ejection that happens, which is basically what we see in the experiment, we believe. Okay? It's very coherent, very laminar. All the plasmoids which bubble off are the same size. And so it makes you wonder then what happens if you drive it harder in the mode where we saw more broadband fluctuations. And what we find is that as we go to larger and larger currents, the fluctuation spectrum becomes much broader band. This is now from the simulations. This is showing from some representative scatter plot for the experiment. And of course, in the simulations, we can drive it harder. So this is what happens if you drive more current in the simulations in Hall MHD. And what you find is, first of all, there's a phase where the equilibrium kind of gets set up, and we've got little plasmoids bursting out and developing. And then one gets this phase where I've got plasmoids of a bunch of different scales being injected continuously, creating the broadband turbulence that we then observe in the experiment, we believe. So the current scaling to some extent is represented, and we think we have something like a transition to two-dimensional turbulence in this configuration. It's interesting to think about what causes the instability. The plasma pressure is large on the closed field lines, and we believe that the modes which are developing are basically ballooning-like instabilities where the magnetic pressure pushes against a weakened magnetic field and it bubbles out and bursts. And if you, in the simulations and in the experiment, the common parameter which seems to be able to bring the simulations and the experiment together is something like essentially a curvature-driven growth term that you might get from MHD. We find that the simulations and the experiments kind of predict the right frequency, where the frequency is set by the growth rate for these instabilities to bubble out. And so then you might ask, does it actually connect to the solar wind in some way? And so you have to know all of the details of what happens with the solar wind, but there's one particular region which seems to resemble our experiment the best, and that would be what are known as helmet streamers. And so the sun has, you can see these, during an eclipse, there is this magnetic geometry which stretches out. And in this region, the question might be, how does plasma go from open field lines from closed field lines close to the sun and fuel the slow solar wind? So this is the solar wind on open field lines is fast. The solar wind which is emitted from the region where the field lines we believe are closed is the slow solar wind. And we're interested in how plasma is transported between here and here. There are great movies. This is from LASCO showing blobs, plasmoids, if you will, that are ejected outward from that region. And what we've done is we've looked at the frequencies of these and tried to compare them to the so this is the sort of thing, these have a 90-minute period, and they propagate outward at about the Alfvén speed from that point. This is from from solar observations. And we've tried as best we can to estimate what the pressure gradients and the magnetic fields and curvature are along something like an ecliptic plane. And we find that with this scaling law that we have from our experiment and the simulations, we get about a 65-minute to 100-minute type scaling for that. And this hasn't been predicted from simulations from the astronomer side. We think this is something that we might be able to contribute to. So it seems to agree fairly well with that. And with that, just summarizing here, we've created a Parker spiral. We have a current sheet at a very high beta, high Alfvén Mach number sheet that becomes dynamic, transitions to turbulence. There's reconnection on the sub-ion scales. These plasmoids are driven by the pressure gradient and bad curvature, and it seems to be consistent with observations. So I will thank you and take questions.
Thank you, Kerry. Okay, questions from the audience? There's one right here. Oh, okay, you can go. Yes.
This is maybe a naive question. You talk about this instability related to curvature. Is this related to the tension from the magnetic field along these curved paths?
We call this a ballooning mode, so the idea tends to be that curvature causes tension that holds the plasma in, and as the curvature becomes weaker and the pressure becomes large enough, it bubbles out in a bursty bubble-like explosion.
Okay, so that sounds like it's vaguely related to the Hoops stress-driven instabilities in polymer flows, where you have tension along curved streamlines.
Magnetic fields and polymers overlap. Definitely.
Very cool.
Okay, let's take a question from Blakesley.
This is really cool. I'm wondering, so when you increase the current, you get this more bursty reconnection that's happening at multiple scales, which somewhat is reminiscent of Lazarian and Vishniac 99. So I'm wondering if you could potentially do some tests of different theories of reconnection, maybe adding in resistivity, because that theory makes very specific predictions about how the reconnection rate should depend on resistivity, how it should scale with Alfvén Mach number, all those sorts of things.
Yeah. So far I've just shown you the first experiments. We haven't gone beyond that yet. We would like to be doing current scalings, go to much higher density if we ever could, get the ion skin depth down, things like that. I mean, I would say this is more, in my view, this is more closely connected to the 2D plasmoid self-generated instability picture. We measure with probes at different toroidal locations. It is very much an axisymmetric bubble that bops out, and that's for whatever it's worth, that's where we are. But yes, of course, we should do lots of scalings and understand it in great detail. I totally agree. Yeah.
Okay, and one more question from the front, and let's have the next speaker set up.
What's the most concrete visual evidence of reconnection you have?
I would say that the fact that these bubbles pop off from the Alfvén point is the topology is changing. So that's reconnection.
And what is the magnetic Reynolds number in your app?
Pretty small. Yeah, Lundquist numbers are of order unity, and so that's like a magnetic Reynolds number. Yeah, in fact, because the Alfvén Mach number is 1, it's identical. Yeah.
Okay, thank you, Kerry. So our next speaker.
Hi, I'm Yuhu, and I'm from the University of Wisconsin-Madison. I'm working with Professor Alex Lazarian, and today I would like to talk about the magnetic field and the turbulence in interstellar media with the velocity gradients technique. And the velocity gradients technique is a new tool developed by our group to study the magnetic field, and there are a lot of people working on it. Here are our group members working on the gradient technique. And we think that's a very interesting topic, and we welcome people to join us. Okay, let's begin the fun. We know that the interstellar media are turbulent and magnetized. And in Chapanov and Lazarian 2010, they shows from the electron density fluctuation, our universe, from the large scales to small scales, are all in turbulent picture. And the magnetic field is also important in the astrophysics process. For example, it controls the galactic dynamics, the evolution of molecular cloud, and the star formation. But what's the correlation between magnetic field and turbulence? In a famous turbulent series, the GS95, they shows that the turbulent eddies are anisotropic. They are elongated with the direction of magnetic field. And later in Lazarian and Wozniak 2099, they explained that the motion of eddies is more likely to be in the direction perpendicular to its local magnetic field. For example, here we use the red and black line to represent the magnetic field lines, and the eddies is going to rotate around the magnetic field. And due to the fast reconnection, with Lazarian and Wozniak shows the eddies also follows the Kolmogorov scale. And in this case, we can easily derive the correlation that the velocity gradients are perpendicular to the local magnetic fields. So that means we just need to rotate the velocity gradients by 90 degrees. We can find the direction of magnetic field. And this phenomenon has been demonstrated in numerical simulation. In Yuan and Lazarian 2017, they use a supersonic and highly magnetized MHD cube. From here, the magnetic field is along the horizontal direction. And if you calculate its velocity gradients, you will find they are indeed perpendicular to magnetic field. And from these slides, begin from these slides, I will rotate the velocity gradients by 90 degrees to align with magnetic field. And for astronomers, you might ask, in which scale does this correlation hold? Actually, the applicable scale for the velocity gradients covers the galactic scale, the interstellar media, and the molecular cloud scale, and also the star or disk scale. And it can also be applied to different types of data. For example, the synchrotron emission with multi-frequency measurements, the neutron hydrogen, including the PPV cube and the column density data. And for molecular cloud, we can use multiple molecular tracers. And this two-fluid ion and neutron simulation is our new process. We expect that we can use the velocity gradients to find the decoupled scale of ion and neutrons. Here are some references, I listed here. And next, I will show you some observational results. The first one is the synchrotron emission. Here we trace the magnetic field, use the synchrotron intensity gradients. The red vectors are the magnetic field from synchrotron intensity gradients, and the blue vectors are the magnetic field from Planck synchrotron polarization. From this figure, we can see that these two vectors align with each other very well. That means our synchrotron intensity gradient can actually trace the magnetic field. And more importantly, there's no need to correct for the further rotation for synchrotron intensity gradients. And as for the velocity gradients in the neutron hydrogen data, the VGT, the velocity gradients technique, can help to remove the contamination from galactic foreground. It's known that the galactic foreground blocks our way to detect the same B mode. But our current measurement from Planck dust polarization is insensitive in high latitude regions. But however, the velocity gradients provide one solution. It can work also in the high latitude region. Here, the top figures is the magnetic field from the velocity gradients, and the bottom figure shows the magnetic from Planck dust polarization. This shows very good agreement, and if we calculate its power spectrum for the B mode and E mode, they also show similar result. You can see from the ratio of the B mode and E mode, they agree with the result from the Planck polarization. And in addition to the two-dimensional magnetic field tracing, we can also go further And we can construct the three-dimensional magnetic field model from velocity gradients. With the assistance of galactic rotation curve, we can reverse the spatial coordinates of the H1 PPV cube in our galaxy. And the application of VGT in those PPV cube will tell us the three-dimensional distribution of magnetic field in our galaxy. And here we also compare our result with the stellar polarization. The white point means they shows very good agreement, and the dark point means there is a disagreement. We can see in most of regions, the velocity gradients align with magnetic field, with the magnetic field from stellar polarization. But there also exists disagreement. Why? Please do not forget the existence of molecular cloud. In molecular cloud, the physical properties is different. To construct the three-dimensional magnetic field model in molecular cloud, we actually need the different molecular tracers, because different molecular tracers corresponds to different density regions of the molecular cloud. For example, the 12 cell, it can trace the outer layer of the molecular cloud, and the trace HNC or C18O, they can trace the inner part of molecular cloud. The application of a VGT to those different molecular cloud can therefore tell us about the three-dimensional magnetic field in molecular cloud. And these also are the advantages of velocity gradients, because in the traditional method from the dust polarization, we can only get the three-dimensional information about the magnetic field. But from velocity gradients, we can get both two-dimensional and three-dimensional magnetic field. And in addition to the magnetic field tracing, we can even go to calculate the alpha 1 Mach number, which is negatively proportional to the magnetic field strength from velocity gradients. In case of a strong magnetic field with a small ma, the orientation of velocity gradients is highly compressed by the magnetic field. However, for a weak magnetic field case, the orientation of velocity gradients gets more dispersed. And we find actually there is a clearly power law between the MA and the histogram of the velocity gradients orientation. Here T is the maximum value of the histogram and B is the minimum value. And from those two formulas, what can we do? We can get the MA distribution in molecular cloud. Here I show an example from the torus molecular cloud traced by 13CO. And we introduce the bow tie mark to indicate, to represent our result. The direction of the mark means the direction of gradients, and the color means the magnetization level. And we make a comparison with the Planck polarization. We see in terms of the magnetic field tracing, they show very high agreement. And if we are going to predict the global MA, we plot the histogram of MA distribution. We can find that the MA calculated from the velocity gradients is agree with the one from the dot polarization. And this result has been published in Nature Astronomy, and the VGT has been applied to different molecular cloud. For example, the Taurus, Perseus, Serpens, Venus, and L5051. And until now, I'm always talking about comparison with the Planck polarization. But can we do something more that polarization cannot do? For example, the Smith cloud. Smith cloud is a high-velocity diffuse H1 cloud. It locates at the boundary of our galaxy. So in this case, its polarization is dominated by the galactic foreground, and we cannot study its magnetic field from dust polarization. But that's not the case for the velocity gradients. Using the H1 data from Smith clouds and use the velocity gradients, we give the first prediction of the magnetic field morphology in Smith cloud, and also the calculation of alpha Mach number. We use the alpha Mach number MA is approximately 0.68, and the calculation of the magnetic strength shows that the magnetic field is larger than 3 megagauss, and those calculation consist with the estimation from here at all 2013 from the farther rotations. And as my final part of my talk, I will introduce some special application of velocity gradients. Here let's talk about, we can derive the sonic Mach number from the gradient amplitude. From the numerical simulation, we find that with the decreasing of the sonic Mach number ms from left to right, the filament of gradient amplitude becomes thicker. And this is also true for the intensity gradients, velocity gradients, and the polarization gradients. And similar to the calculation of MA, we still find there exists a correlation between the sigma is the dispersion of the gradient amplitude, and mu is the mean value of gradient amplitude. There exists a correlation between MA's as two values. And from this formula, then we can predict the sonic Mach number distribution in the sky. Here is an example from the GAFA H1 survey, high latitude regions H1 data. And our prediction of the MS shows most regions shows the MS less than 1. They are subsonic. And this is what we expect for the warm neutral media in high latitude regions. And the second one is we can go further to identify the gravitational collapsing regions from the gradient orientation. Because in collapsing regions, the safe gravity dominates over the turbulence. And in this case, the inflow motion will flip the gradient's direction by 90 degrees. Therefore, you can see from the figure, in diffuse region, they align with magnetic field, but in the safe gravity region, the gradients are flipped by 90 degrees. From this feature, we can then go to identify the gravitational collapsing region. And here are one example from Serpent's molecular cloud. And the blue vector is magnetic field from Planck, and the red vector is from magnetic field from the VGT. And we see at the most dense part of this molecular cloud, the gradients get to perpendicular to the magnetic field. We therefore expect that region is under the gravitational collapsing. And in addition to the velocity gradients, we also have the information about intensity gradients. And because the intensity structure the shock of intensity structure gets to perpendicular to magnetic field. And that indicates the intensity gradients is actually aligned with magnetic field. Of course, here I rotated it by 90 degrees for both intensity gradients and the velocity gradients. The red vector is the intensity gradients, and the yellow vector is the velocity gradients. We can see that the velocity gradients gets perpendicular to intensity gradients. So that provides a new way to identify the shocks in the interstellar medium. Okay, that's a summary of my talk. Based on our advanced understanding of MHD turbulence, the gradient technique has been developed into a big ecosystem, which can help us to study the magnetic field, the turbulence, and also how to find the transitional regions in molecular cloud. That would be very interesting.
Okay, thank you, Yue. Are there any questions from the audience? Let's have Shmuel.
So I wonder about when you apply this technique to H1,
Mm-hmm.
how do you deal with the fact that H1 in the interstellar medium is multi-phased? So you'd have two things. One, transition from supersonic in the cold to subsonic in the warm neutral medium. And then also the fact that the more cold and dense H1 is usually kind of enveloping molecular clouds, when the warm H1 is more diffuse and volume time.
And that's a good question. And that's what we are doing now at the multi-phase H1 data in simulations. And we find that actually the it depends on the thickness of the velocity channels. And in the very thin velocity channels, that the cold neutral media most likely to locate at the thin velocity channel. But in that case, they are also elongated with the magnetic field because of the velocity caustic effect. That's been explained in Lazarian and Pogosyan 2000.
Okay, any other questions? Leslie, you had one?
Just wondering, like in the application to the Smith cloud, if you think any of the gradient information could also be due to some kind of ram pressure effects, because the Smith cloud is, I guess, infalling into the galaxy. So how that maybe biases the measurement of the alpha Mach number from gradients.
Alpha Mach number. I think you are talking about that. Maybe the galactic gravity will bend the magnetic field in in the Smith cloud, and that's also interesting questions. But we didn't consider this effect. We got calculated from the channel cyclofilm method and compare with our result with the one from synchrotron, the Faraday rotation, and we get the similar result. And we think that there are a little effect from the galaxy.
Okay, thank you. Yeah, and let's thank our speaker again.
Okay, so thank you very much. I want to thank the organizers for giving me a chance to be in this special conference that is really interdisciplinary. And I think it's very exciting to hear about turbulence from different fields. My name is Shmuel Bialy, and I'm coming from snowy Boston. I came like this. This was my vehicle when I came here. And my talk will be concentrated based on these two papers, 1 or 2 years ago with Blakesley, and also now also with Blakesley and Emil Sternberg, my former PhD advisor in Tel Aviv. Now I'm at the CFA in Harvard, and also other collaborators. And the idea here is really, I think it's quite interesting that it connects several fields of chemistry, astrochemistry, and turbulence to study the structure of turbulence in the interstellar medium. So this thing here, the interstellar medium, the ISM, and that's the background image here. That's an example of a piece of the interstellar medium of our galaxy. That's the Carina Nebula. And I think it's really just nice to stare at it, but I'll continue to talk and, and won't let you stare at it. So just to start with a short overview, because we come from different fields, about the interstellar medium and the turbulence in it. So in the interstellar medium, flows become very rapidly turbulent because the high Reynolds number, if you wish, you can just very easily estimate. The Reynolds number is about 10 to the 5, 10 to the 6, sometimes even more. So any flow become very turbulent, and it may be supersonic or subsonic depending on the phase of the ISM, and that was my previous question that I asked about the H1, for example, because we know that the H1 can be, the atomic hydrogen, may be either quite warm, about 10 to the 4 degrees, or cold, about 100 degrees. That's because we have different cooling mechanisms in the interstellar medium and heating mechanisms from stellar UV light and cooling from line emission, which cools the gas to these temperatures. So the cold gas is usually supersonic, the warm is subsonic, and the densities are quite low, much lower than what we hear in these experiments. So high density would be 100 particles per centimeter cube, and low density is about 1 particle per centimeter cube. And we still call it gas, not vacuum. And importantly, the stars form in this cold atomic molecular clouds that are somewhat denser and are known to be very turbulent and supersonic. And later, Vadim will also tell us about the importance of turbulence in regulating the rate of star formation in galaxies. So turbulence plays a very crucial role in astrophysics. So the main goal here is, can we somehow better constrain the properties of turbulence? And with special focus in this talk on what can be the main driver of turbulence in galaxies and the interstellar medium. Is it driven on large scales from the gravitational potential of the galaxy that induce motions? Or is it more on smaller scales, what we call feedback from supernova, or even outflows and winds from stars? And the idea is as follows, just to sketch. So we have the turbulence, and the turbulence, when supersonic, it produces density fluctuations because it's compressible turbulence. And now when we have density fluctuations, because chemical reactions are very sensitive to the density, this also produces fluctuations in the abundances of various chemical species, molecules, ions, etc. Now, these chemicals and the abundances of these things, we can observe chemicals with spectroscopy, with space-based telescopes. So if we observe the chemical reaction, the chemical abundances, we can reverse the arrows and use the fluctuations in the chemical abundances to tell us something about the density structure, and then back to tell us something about the turbulence. So that's a basic idea. And then if we constrain this, we can maybe say something about the driver of turbulence in the ISM. So let me jump in directly to our spherical cow model. And how do we do this? So what we do, we run a hydrodynamic simulation, or MHD, magnetohydrodynamic simulation box. The box is driven on large scale, and the turbulence naturally cascades to smaller and smaller scales. We have solenoidal driving and isothermal equation of state. And importantly, I'll focus here on these two parameters: the sonic Mach number, which kind of tells you the strength of the turbulence, and the driving scale, the scale where you drive the turbulence. That tells you what would be the scale of the density fluctuations. The larger the driving scale, that would be also the larger scale density fluctuations, and small will give you a smaller scale of density fluctuations. So our spherical cow turns into a box cow, and that's the box cow. So this is an image of the density field when integrated along one axis. Let's call it the line of sight, what you'd see if you have a telescope pointing into this turbulent box. Now, what we assume that there's a UV light irradiating this simulation and cosmic rays also. And now we solve a model of chemical reactions. That model include a gas phase reaction and dust reactions, along with UV radiation, photodissociation of molecules, cosmic ray ionization of molecules and ions, to calculate the abundances of various chemical species, molecules, atoms, ions. So importantly, this density field is the input for our chemical model. So in the end, the abundances, as I also mentioned before, the abundances of various molecules depend on this density field, which in turn depend on the turbulent parameters such as the Mach number and the driving scale. Then we take these calculated abundances and compare them with observations. That's the idea. Importantly, we have to run several simulations because we want to constrain the turbulent parameters. So we run 6 simulation boxes for different combinations of driving scale, L drive, and Mach numbers. So we have 6 boxes like this. And actually, I have more boxes because we have the different molecules and atoms. For each of them, we calculate a box like this, a map of the abundance integrated along line of sight. We always have to integrate along one axis because that's what we see in observations. We never see the volume density of species. We always see integrated column densities. So let me jump now to the results, and I want to focus on 3 sets of results. One is what is the role of the sonic Mach number in our simulations. Then what's the role of the driving scale? And finally, to compare with observations and see what we can learn from them. Okay, so here I show an example of what you get for the H1 from the atomic hydrogen. Again, we take the box, we integrate along one axis, we get the H1 column density, that's number of atomic hydrogen per centimeter square, or maybe I should say inch square, or in the US. I don't know. I won't do that. So that's the number of H per centimeter square H atoms integrating along one line of sight. And you see some amount of fluctuations. Typical numbers are like 10 to the 20 atoms per centimeter cube square. And that's the PDF. It's quite narrow. Now, what happened when we changed the Mach number? So what I showed before, this was a sonic Mach number of half, so that's pressure dominated. Now, when we go to supersonic turbulence, now density fluctuations really develop, the turbulence become compressible. And as a result, we also have fluctuations in the abundance of H, atomic hydrogen, and H2. And now we have, really, we see in the map, strong fluctuations between different regions, different lines of sight. The PDF become narrow, the PDF become wide. So generally, as the Mach number increases, strong density fluctuation develop, and the dispersion in the column density of atomic hydrogen becomes large. Now, what's the effect of the driving scale? And I think it's quite important to also focus on that, because often I feel, at least in astrophysics, people sometimes neglect this. They very often talk about the Mach number, sometimes about the beta parameter, but not so much about the scale of driving. And this is also very important because we have now here, we have an averaging effect. When the driving scale is large, the scale of each density fluctuation, and when I say scale of density fluctuation, I mean maybe the scale over which the density is correlated. The scale of each density fluctuation is large, and as we look in different lines of sight, we really, in each line of sight, we really see just one or several density fluctuations, not many. As we decrease the driving scale, we have many, many small density fluctuations. As we integrate along a line of sight, we integrate them over. Positive and negative density fluctuations average out, and different lines of sight become more alike. And that's, for that reason, this H1 map becomes more uniform. The density fluctuations here are smaller just because they are averaged out as we integrate along line of sight, and the PDF becomes narrow. So really, the PDF can be narrow or wide, not just because effects of Mach number, but also because of the scale of density fluctuations, the scale of turbulence driving. To summarize these 2 points, the dispersion in H1, but also in other species, I just show here H1 as an example, increases as the Mach number increases because the fluctuation intensity increases. And it increases as the driving scale increases because the fluctuation length scale or coherence scale increases. Now let's apply this to observations. Let's see what we have in real observations. So in this quite busy plot, what I show is 3 models for the 3 rows. This is a model of the subsonic box. This is a supersonic, but driven on small scales. And this is supersonic driven on large scales. And in each row here is a different molecular ion species, argonium H+, OH+, H2O+. This is some molecular ions that are observed in the interstellar medium. And this is mutual PDF of these molecular ions with the column density of H1 that we saw before. So that's mutual PDF, but you can really concentrate on the x-axis, the width of the PDF. Here, the 3 regions here is the 1, 2, and 3 sigma, so 68, 95, and 97 percentiles of the probability distribution function of these molecular ions. And this crosses our observations from the Herschel Space Telescope towards different locations in our galaxy. And what we can see is clearly the subsonic case the observations have much larger dispersion than what predicted by theory if we take the subsonic simulation. As we increase this, the Mach number from subsonic to supersonic, the PDF becomes wider, but still not wide enough. And really to account and to explain the large dispersion seen in the observations, we need not only supersonic, but also large-scale turbulence driving. So really, this is the one that really best matches the observations. Still, it's not a perfect match. Our model is still very simplified. It's isothermal turbulence is a box. The interstellar medium is not a box. And other assumptions that are made in our simulation. But this is just to show the general effect of the Mach number and the driving scale. So based on observations and model, we can say that supersonic large-scale driven turbulence best matches the observations. But, okay, there's always a but. And there's, of course, few caveats to the study. We're again in the United States, so maybe I should say future prospect. So first thing is, I think that future prospect, some future developments that might occur is to include time-dependent chemistry. So here in this model, we assumed chemical equilibrium. This might be a good assumption in some cases, but not always. So depending on the time scale of the turbulent motions, if it becomes short compared to the chemical reaction time scale, then the chemistry can be out of chemical equilibrium. Then, as I asked, and now I can also ask myself, what about the ISM being not isothermal? We have different phases, the warm and cold, and this can really have a huge effect on the abundances of molecules and ions. For example, you don't expect to get any molecules whatsoever in the warm neutral medium. Then we can have also fluctuations in other things. I focused here on turbulence, but the abundances of molecules depend also on the UV radiation strength, on the cosmic ray ionization rate, which can also fluctuate between locations in the galaxy. I would like to say a few more words on this, because really it's kind of, we have a degeneracy here, because the abundances of these molecules, argonium H+, OH+, H2+, that I showed, really depend on the cosmic ray ionization rate. But on the other hand, the way we know what's the cosmic ray ionization rate in our galaxy is also from these same molecules. So we need a different tracer of the cosmic ray ionization rate if we want to break this degeneracy between turbulence and fluctuation in the cosmic ray ionization rate. And recently I proposed such a new method, still to be explored in observations. And the idea is to use H2, molecular hydrogen, which is the main constituent of the gas in molecular clouds, as a probe of cosmic rays. The idea is cosmic rays come, hit an H2 molecule, excited. Then the H2 molecule, when it relaxes to the ground state, it emits a photon or vibrational line in the infrared. And if we observe this photon, we can constrain the excitation rate, which is the cosmic ray ionization rate. So this might be a new method to constrain the cosmic ray ionization rate in the galaxy, in molecular clouds. Once we do all this, once all is checked, we can go to the last step and use this method of chemical abundances to constrain turbulence properties and the driving of turbulence in the interstellar medium. Thank you.
Thank you, Shmuel. Any questions? Is that one there?
Yeah. So even incompressible turbulence can also drive density fluctuations by solenoidal motions. So my first question is whether it's possible to distinguish, or whether it's important to distinguish the density fluctuations coming from solenoidal motions and compressible motions in turbulence. And the second question is, in your comparison with observations, that is very interesting. how can you tell that these large-scale density fluctuations and small-scale density fluctuations, they come from the same cascade?
Okay, so I first try to answer your first question. So first of all, yes, also in the subsonic. First of all, in our simulations, it's solenoidal driving. And also in the subsonic simulations, we do get density fluctuations. And that's why you see here fluctuations in the column density, which is lower than what, even this is high. If you look at the density field, it's even more extreme. This is already integrated along line of sight. So you do have it, and you have a continuous increase in the amount of fluctuations as you increase the subsonic. It's not like abrupt from homogeneous to suddenly you get fluctuations. Indeed, in astrophysics, you also have this magical B parameter, which connects between the amount of density, connects between the dispersion of density and the Mach number, and this depends on the type of driving, if it's solenoidal or compressional. So it's kind of degenerate. It's true. It's very hard to disentangle. I don't have a good answer for this. Like, do you have an idea?
Yeah, I mean, basically the PDF depends on both of these things. So you have
So
an
it's kind of
effective Mach
degenerate.
number that measures the overall compression, whether it's from the type of driving mechanism or from the Mach number.
Yeah, so it's kind of degenerate. Yeah.
Okay, I see there's lots of questions. Time for one more. Let's have Sauro.
One is very basic, probably I misunderstood. Is there any real feedback loop from the chemistry to the turbulence?
The chemistry to the turbulence, not so much. The chemistry is mainly a tracer.
Because in one of your first slides, there was a reverse loop.
Oh, no. The reverse loop is just that we can, this is the physics, go to one direction, and then this is the experiment. We can use this to study the physics. There's no, I mean, there's small effect, but it's not serious.
Why are the density fluctuation negatively skewed?
Well, it's kind of more complicated than what I outlined in the talk, because H1 here is really also very strongly affected by the UV radiation. So it's not just what we see here is not just the density fluctuations. It's the combined effect of the density fluctuations and the chemistry, which has to do with how the UV radiation is absorbed as it gets further and further, deeper and deeper into the cloud. This is a very nonlinear process. So it's a combined effect of chemistry, if you call it chemistry or whatever you call it, and turbulence.
That I understand, but the fact that the skewness as a sign usually is accrued to some big physical mechanism.
I think it has to do with the physical mechanism of H2 photodissociation and H1 formation through this photodissociation, and we kind of try to explain this in this first paper. It's kind of tangled with the turbulence, so it's hard to give a very straight explanation, but I think it has to do with this physics.
Okay, thank you, Shmuel. Let's have Vadim come up.
Yeah, thank you so much. And I would like to thank the organizers for giving me this great opportunity to give a talk at this conference. And I'll be talking about the star formation in galaxies. And just now we had this great introduction to the multi-phase nature of the interstellar medium. And yesterday we had several talks introducing the role of turbulence in star formation. And it is clear that turbulence plays a crucial role in this process, and it's enough just to look at the typical sites, the environment in which gas is converted into stars in galaxies, so like this in the ground, so we can stare at it a little bit more. This is Svetlana Doradus in this case, and just to give you a sense of scales, we are looking here at a tiny patch of the ISM comparable to this tiny square on the face-on image of a galaxy. I don't know if you can see it, but it was like the smallest square I could put in PowerPoint. But this is roughly the scales we're talking about. And the stars in this environment form on even smaller scales. So individual stars form from a collapse of self-rotating cores on really tiny scales, and scales 1,000 times smaller than this size. And the formation of this self-gravitating cores is facilitated by a turbulent, supersonic turbulent cascade that extends out to much larger scales, to scales of entire star-forming regions and even larger galactic scales. And then what makes this problem even more complicated is that these tiny scales can affect large scales because of the so-called stellar feedback. So stars, young stars can inject a lot of energy and momentum because they have very strong radiation, stellar winds, and frequent explosions of supernova can destroy the star-forming regions, drive large-scale turbulence, and even remove gas away from the galaxies. So I myself work in galaxy simulations, and in galaxy simulations, modeling the star formation and stellar feedback is the key challenge nowadays. And this is because in galaxy simulations on these scales, we never see a beautiful and complex picture like this. We have to deal with something like this. So this is a typical resolution of the simulation. So we have no information about this complex dynamics and structure of gas on unresolved scale. So modeling star formation necessarily requires subgrid prescriptions. In other words, we need to tell our simulation what the star formation rate in each resolution element given the resolved properties of gas. And one of the very common ways to do this is to just parameterize local star formation rate with the so-called star formation efficiency, which just a parameter which tells us what fraction of gas mass in each cell is converted into stars on one freefall time. And this freefall time, it depends on gas density and it's a time scale on which gravitational processes operate. So in simulations, this star formation is usually allowed only in gas that satisfies some criteria, such as gas must be denser than some threshold or colder than some temperature threshold. And different simulations make very different assumptions about what these thresholds are, and even the value of the star formation efficiency per freefall time can also be very different from simulation to simulation. But almost always it's assumed to be constant in space and time. In contrast to this, theory tells us that the star formation efficiency is not a fundamental constant of the universe. It strongly depends on properties of turbulence in star-forming gas. And for example, this plot shows results of MHD simulations of supersonic turbulence with cell gravity, and where they find that the star formation efficiency is a strong exponential function of the so-called viral parameter of turbulence. So viral parameter for cell gravitational turbulence tells us the relative importance of turbulence support and the self-gravity of gas. And when support becomes stronger, star formation efficiency is exponentially suppressed. And there is similar strong dependence on viral parameter is also predicted by analytical models of star formation in turbulent gas. And in principle, we can use models like this in galaxy scale simulations as a subgrid prescription. So we can assume that something like this happens in each resolution element and use prescriptions to relate properties of turbulence to star formation, local star formation. But the problem is that we need to model turbulence on unresolved scales. And to do this, we use this approach called large eddy simulations. And again, yesterday there was a nice introduction into methods like this. So methods like this are widely used in simulation of terrestrial flows and aerospace engineering. And I'll show one of the first applications in galaxy formation simulations. And the basic idea is that we can solve a set of filtered hydrodynamical equations which describe result flow and also evolution of turbulent energy on unresolved scales. And the terms which describe the relation between resolved and unresolved scales can be calibrated in direct simulations, high-resolution simulations of turbulence. So this is the result, what we get if we model a galaxy like ours using this subgrid model for turbulence. And this is the prediction for turbulent velocity in each resolution element. So now we can use this information, combine it with the gas density and temperature to figure out what the viral parameter on unresolved scales, and use it to model stars in the galaxy. So this panel shows where the young stars are, and we can see that stars are forming along this dense spiral arms. And we can also see the effects of feedback on the overall structure of interstellar medium. So you can see that young stars, they explode as supernova, they create these bubbles of very hot and also very turbulent gas, and they destroy some of this dense gas and create this overall flocculent structure with turbulence on large scales.
Stars in this?
Sorry?
Where are the stars?
So stars are here. So this is at each point here is a like young star, which is younger than 20 million years. So these are the locations where stars are formed. Yeah, so we can look at more details, the predictions in terms of local efficiency in this model, and it's shown here. And again, we can see that stars are forming only in dense spiral arm in dense gas, and this happens automatically without requiring any thresholds, just because diffuse gas is well supported by thermal motions, so it's non-star forming according to this model. In addition to this, in cold and dense gas, the average values of efficiencies are over 1%, which is similar to what is observed in real star-forming regions. And this is the output of the model, because the model was calibrated on direct simulation of turbulence, which know nothing about star formation in galaxies. So it's encouraging that when we apply it in galaxy scale simulations, it gives us the correct answer. And in addition to this, it also tells us that efficiency can vary by orders of magnitude, even in cold and dense gas. So as an extreme example, we can look at these two spiral arms. They both have the similar density, so if we use the density threshold to define star-forming gas, we would assign the same efficiency of star formation to them. But according to this model, one of these arms forms stars very efficiently, while the other one doesn't form stars at all. And this is just because of the variation in turbulence support, which in this case reflects difference in compression rate in these two spiral arms. And there are similar variations of local star formation efficiency now is seen in various blind surveys of star formation in galaxies. So this means that turbulence plays a major role in setting star formation efficiencies locally in star forming gas on small scales. And now the question we can ask is how this all propagates to larger scales. So how star formation that we see on large scales globally in the galaxies, how it relates to star formation on small scales and the processes that drive gas evolution on small scales. And to do this, we can look at the evolution of gas in this plane of gas density and total velocity dispersion, which includes both turbulent and thermal motions. And this shaded region shows the region of phase space where the viral parameter is low enough so that gas can form stars, and in the rest of the ice in the stellar medium, it's non-star forming. It's a simulation, so we can trace the evolution of individual gas parcels. And this is how this evolution looks like. So this movie shows the evolution on one rotation of the galaxy, and we can see that on this time scale, gas rapidly switches back and forth between star-forming and non-star-forming states. So what happens is when gas approaches the star-forming state, efficient stellar feedback and other processes that destroy star-forming regions very quickly remove it back into non-star-forming state. So it has to start the entire cycle from the beginning, and on each cycle, gas spends only a small fraction of time in a star-forming state, and therefore it can convert only a small fraction of mass into stars. So this explains why globally star formation is so inefficient, and global consumption takes many dynamical cycles. And it can be expressed actually analytically. If we have this picture in mind, we can write down this so-called gas depletion time, which is just the ratio of gas mass and star formation rate. It's the time scale in which all gas mass will be converted into stars. And we can rewrite it as a depletion time only in star-forming state, divided by the mass fraction of gas in the state. Depletion time of star-forming gas, it depends on properties of star-forming regions, such as local efficiencies of star formation. But the mass fraction of gas in this state depends on the process that supply and destroy star-forming regions. So we can write it as a ratio of time scales that gas spends in these two states. And then we can combine these two equations and get the simple expression for depletion times, which tells us that the global depletion time of gas is a depletion time in star-forming state, plus the total time that gas spends outside of star-forming regions. And the duration of each cycle is set by dynamical timescales in the interstellar medium, is TNSF. And the number of cycles is set by the ratio of depletion time in star-forming state, which is long because star formation is locally inefficient, and the typical duration of star-forming stages, which is short because of the efficient feedback. So this ratio becomes very large. So the situation here is very similar to what is going on in soccer, And soccer is also they're inefficient, and the typical time crossing for players is order of dozen seconds. But at the same time, the overall score at the end of the game is very low. So it means that the time scale on which goals are scored is very long compared to this dynamical time scale. So it means that efficiency of scoring is very low. And the origin of this inefficiency is very similar to the efficiency of star formation. And what happens is that when fans of one team approach the goals of the other team, they don't just go ahead and score. Instead, they face strong feedback from the defense. And as a result, they have very low probability of scoring on one such approach. So they spend very small amount of time close to the penalty area, and therefore they have to cycle through a large number of attempts before they accumulate enough probability and eventually score. And exactly the same thing happens with atoms in the ISM. You can think of each individual atom going through this subsequent stages where it's in star-forming state, and it has very low probability to end up in a star on one such stage, and so they have to cycle through many attempts. And this expression simply tells us the relation between different time scales in this process. And we can use it, for example, to understand what's the role of the turbulence in setting this global star formation rates in large scales. So as I said, in principle, turbulence affects all these relevant time scales. So for example, as I said before, the local depletion time is very sensitive to the local turbulent support in star-forming regions. So stronger turbulent support can reduce star formation efficiency and increase local depletion time scale. So this means that there can be abundant dense and molecular gas in galaxies, which is non-star forming just because of strong turbulent support. And nowadays there are observational evidence that such gas exists. But in addition to this, turbulence can also affect the transitions between star-forming and non-star forming states. So for example, the large-scale turbulence can move gas around this plane, and in dense gas, the transition to the star-forming state is set by the decay of turbulence locally in star-forming regions. At the same time, the turbulence can make stellar feedback more efficient in destroying removing star-forming gas from the star-forming state, because now stellar feedback can just drive turbulence to stop star formation in star-forming regions instead of requiring to destroy the entire region. And this can be much more efficient. An example where these two effects become important is the observed relation between star formation rates and dense and molecular gas. So if we look at the large enough patches in nearby observed galaxies, we can see that the depletion time of dense gas is fairly constant, of order of, for molecular gases of order of 2 billions of years, and it's independent of how much molecular gas is there in these patches of the ISM. And in the simulations with the turbulent-based star formation, we can get very similar constant depletion time of molecular gas, and we can understand why it's constant. But the thing which is interesting is that if we run exactly the same simulation, only changing the way how stars are forming. So if we use just a common prescription based on a density threshold and fixed efficiency, we get much steeper relation, which is inconsistent with observations. And this is exactly because of this difference in how gas transits between star-forming and non-star-forming states in this case, because now, in order to become star-forming, gas must be compressed to high densities, and this happens on much longer time scales in diffuse gas, while for turbulent-based star formation, this still happens on local crossing time turbulence on which turbulence decays. So this happens very rapidly. So I'll switch to my summary. So the turbulent-based star formation model predicts wide variation of star formation efficiency in space and time, and it doesn't require any assumptions about thresholds and efficiency of star formation. In addition to these local effects of turbulence, it also has important effects on larger scales because it affects the transitions between star-forming and non-star-forming states. And one example where it becomes important is this relation between molecular and dense gas and star formation rates. Thank you.
Thank you, Vadim. Let's take some questions. How about Daisuke?
So I guess in ISM, other non-stormal pressure support like cosmic ray and magnetic fields are also probably just as important as turbulence. Can you say a few words about the implications of your work, which does not include those components.
Yeah, in principle, in principle, this is just a framework which relates all these relevant timescales, and the actual values of these timescales can be set by different processes. So, for example, they can be in these simulations they're affected by process like large-scale turbulence or compression of gas in spiral arms. But if there were also magnetic fields, they could also be affected by the time which gas need to get rid of magnetic support, or it can affect these timescales as well. Yeah.
Okay. Question from the left side. Yeah, you. Yes.
Oh, this is probably a basic question, but do you know if I've read studies that the turbulence in the interstellar medium are probably cosmograph-like power spectrum, or probably a little steeper. Does turbulence by star formation and gravity and the interplay between both, do you know what the power spectrum of the turbulence that produces is like? Is it also cosmograph-like, or is it a different power spectrum than that?
I'm not sure about the difference in the effect on the power spectrum, but I think one of the way to distinguish between these effects is, for example, to look at the different. If it's like look at the differences, different scalings between, like, let's say things like gas fractions and star formation rates, because if the star formation is turbulence regulated, there will be like different predictions for the scalings, and I think it's related to the work which Blakesley were doing. So, but I'm not sure about. I think I'm not sure if there will be like strong dependence in the power spectrum if it's like turbulence.
Follow up from Zoom.
Oh yes, please go ahead.
Yeah, Mordecai Maclow here.
Oh.
So there are potentially multiple drivers. The diffuse ISM may be supernova and feedback driven, while the most observed turbulence in the clouds may well be driven by hierarchical contraction. However, models, for example, by Ibanez Mejia and myself and others, show that the power spectrum, it's still a cascade, so you still get something that looks like turbulence, even though the driver may have switched in the dense gas to something that's more or less decoupled from the rarefied gas.
Mm-hmm.
To follow up on that with a question, in your alpha Beer model, are you resolving far enough down to see the gravitational contraction of the dense gas? Because otherwise you may end up with alpha Beer that's too low.
Yeah, it's a great question. So actually, no, in these simulations we, so this dashed line in this, yeah. So we do not resolve viral parameters close to 1. So the lowest ones are about viral parameters of 3. But it depends on the resolution of the simulation. But also, if we look at the results of these simulations, they actually do a parameter study where they look at the range of viral parameters. And so at the viral parameter of close to 1, the efficiencies are high, but they're still like not super high, or a few dozen %. But at higher viral parameters, the star formation efficiency is still sufficiently large. So it's, for example, a viral parameter of 10, it's of the order of 1%. This is just because in this turbulent structure, there's always, even if it's super viral, there is a substructure which can be subviral and form stars. Yeah. So it's a question of scale. Yeah.
Okay, thank you. So the clock up there says coffee. So I think still lots of questions. So I encourage everyone to please seek out the speakers and talk to them. Thank you.